This is a lecture about interfacing a numeric keypad to the MB90F387S using the 740C922 keypad encoder. So let me just tell you the content of this lecture. First, we're going to study the keypad and how the keypad is constructed, and then we will study also how it is controlled. How are you going to identify the switch being pressed, and how are we going to easily acquire the address of the keys by using a keypad encoder. So let's begin with the numeric keypad. The numeric keypad is the most common input device in embedded systems application, and it follows the telephony standard layout. It may be 3 by 4 or 4 by 4. That means that it's 3 columns by 4 rows or 4 columns by 4 rows. The construction of the keypad is using an array of push button switches with common columns and rows, which eliminates the individual controls of all switches. So for example, if you have a 4 by 4 switch, or a keypad, that would mean that there are 16 individual keys and 16 individual switches as well. So it would require 16 I/O ports just to um, interface the keypad to the microcontroller. Now, 16 I/O ports, yes, that's a lot. And in some microcontrollers, they might not have that much GPIO port. So one way of eliminating the number of GPIO ports needed is to use uh, an is to lay out the switches in a matrix or using an encoder circuitry. But let's just look at the physical layout of the switch. You have here some examples. So you have a couple of examples uh, from a 4 by 4 keypad layout. As you can see, there are 4 columns and 4 rows. And another example would be the 3 by 4. Now looking at these keypad examples, particularly the 3 by 4 follows the telephony layout. So in telephones have this layout, the dialer pad on the telephones, and the variations of the other keypads, basically the layout is the same, but the keys just printed on the buttons may also vary. Some keypads have more than 4 columns, like in this example here, and some keypads are the same 4 by 4, but the functions or the buttons are different. But in any way, the 4 by 4 keypads are basically constructed the same. They just differ in the printed keys here, which represents the function of the key. So the switch are connected in a matrix, which we designate some columns and rows, and each switch connects to a row and a column. So for example, if you look at switch 1 is connected to column 1 and row 1. And switch 1, 2, 3, and 4 are connected commonly to row 1, while switch 1, 5, 4, and 8 is in common connection at column 1. So it's true for all the switches that the switches are connected in a certain column and a certain row. And each row or column has several switches connected on it. So let's say, for example, if you're wondering, how are you going to control the keypad? How are you going to identify which switch is connected? Well, first of all, we have to uh, study uh, the construction. Okay, so the construction is basically that each switch is connected to a common column row. Now, if we pass a current, let's say for example in column 1, obviously the current would pass through the entire column 1. And if you press switch 1, the column would flow from column 1 to row 1. Or you press switch 2, the column or the current would flow from column 1 to row 2. However, that is just for column 1. Column 2, if we pass through a current from column 2, the same thing would happen. Let's say, for example, column 2, press switch 2, the current would flow from column 2 to row 1. Or if you press switch 14, the current would flow through from column 2 to row 4. Now that you have understood the construction of the numeric keypad in terms of the push button switches, let us now try to understand how to control the keypad. The easiest way is to supply one of the columns with logic 1 while the rest is logic 0. It means that only one column is supplied with current, and if one of the buttons in that column is pressed, the current will flow to the corresponding row, and therefore the column and row data will now be used to identify the specific key that's being pressed. Then we move to the next column and read the row data. So we have to supply each column with at least logic 1, and then we move to the next column, and so on and so forth. Now remember, only one column should be supplied with logic 1, while the rest is logic 0. So as an example, we'll have the first column energized. We will try to assume that the first column is the most significant bit and the fourth column is the least significant bit. So the columns 2, 3, and 4 does not have any current, only column 1. So if any of switches 1, 5, and 9, and 13 will be pressed, the current would flow through either row 1, 2, 3, or 4. So for example, we are going to press switch 5. Pressing switch 5 would allow the current to flow from column 1 to row 2. And if we're going to read the row data, assuming that there is no other current flowing through from any other row, so we'll treat those rows without current flowing through as 0, so therefore the address now would be 0, 1, 0, 0, assuming that this is the most significant bit and the least significant bit. So the column and the row data would now serve as the address of the key that's being pressed. This key is switch number 5, being at column 1, row 2. So this is its corresponding address. Now, we have to move from one column to another column, to another column, to another column. And we have to do this all the time in order for us to scan each column and scan for any key being pressed in each column. So let's say, for example, we moved on and we arrived already at column 3. Okay, but the same concept. Again, if any switches, switch 3, 7, 11, and 15 is pressed, so the column or the current will just flow to the row. In this case, we press switch number 11. Okay, current will flow from column 3 to row 3, and therefore the row address of the switch 11 is 0010, and its column address is 0010. Now, I have compiled a table for the row and column data. So here in the first column, we have the key. Now, in the 4x4 layout, the fourth column is basically just used for the letters A, B, C, and D, while the rest is the numbers and these two symbols here, which is used in telephony. For switch number 1, which is representing key 1, the column address is 100B, such as 4, 7, and asterisk. They share the same column, but they have a different row. Okay, 2580, 2, 5, 8, and 0 shares also the same column as well as 369 and pound sign, and A, B, C, and D. So they just differ in the row. Okay, so to identify which key is being pressed, all you have to do is to um, correspond the column and the row data, and then obviously you will find out which key that's being pressed. So this method, okay, is basically the only solution to identify the key that's being pressed. You should know its column, which column it belongs, and which row it belongs to. So that you can identify the exact switch that's being pressed based on at least based on the layout of the keypad. Now, if we're going to interface this to the microcontroller directly, so here's how we're going to interface this. In this particular example, we are using not a 4x4 keypad, but a 3x4, so 3 columns by 4 rows. Now the same concept, but instead of having 4 columns to scan, you only have 3. So this is a much quicker deal because you don't have an extra column to scan. So you connect that to any of the GPIO ports. In this case, you need only 7 GPIO ports to scan to control the keypad. No? So you supply, this is basically X1, 2, and 3 in the GPIO port here would be output because you are outputting a signal to supply to the columns of the keypad, while Y1, Y2, Y3, and Y4 here are basically input because the signals from Y1, Y2, Y3 would be coming from the keypad. Okay, and the pull down resistors here just ensures that when there's no current, the circuit is not hanging. So we have to pull the IO port to ground to register as a logic 0. Otherwise, the microcontroller will read 1 instead of 0 because this is not TTL, this is CMOS. So in CMOS, any input port that is hanging, the microcontroller would read that as 1, not 0. So to read that as 0, there's no input. Therefore, we have to pull it to ground. Four, three, two, one. The hassle of controlling the keypad being that you have to scan each column and read rows, plus you need to have a lookup table to identify which key is being pressed, might take a toll on the process or uh, the logic of the program, which is running on the microcontroller. So instead, why not just let somebody else do that? And all the microcontroller would do is just read the address of the key that is being pressed. And that's it. So the microcontroller does not have to do the column scanning and reading the row data and looking up to the lookup table to identify which key is being pressed. So to do this, we need to have a device, an integrated circuit that would do exactly those things. And that device is the 74C922 keypad encoder. So it's basically a CMOS keypad encoder that encodes an array of single throw switches or SPST, and the keypad or keyboard scanning is implemented automatically by the integrated circuit. So that is very convenient that the microcontroller does not have to do that. It has an internal debound circuitry that would eliminate the switch bounds for all 16 keys. The data available output returns logic 1 when any of the key is pressed, which would indicate would be a useful signal to the microcontroller that indicates that a key is being pressed. So this is the 74C922, the pinout of the 74C922. It has a total of 18 pins, and the pins 1 to 4 is the connection to the row of the keypad, while pins 7, 8, 10, and 11 for the columns. This is the oscillator, where you have to put a capacitor, and the key bounce mask, basically another uh, oscillator for to eliminate the switch bounce. So you have to supply an oscillator that is 10 times the capacitor as connected here in pin number 5. Output enabled is a pin that allows the data output, the 4-bit output, which is the address of each of the keys. Now this is 4-bit, so 2 to the power of 4 is 16, so therefore there are 16 individual addresses here, or 16 keys. And this particular IC is designed for 4x4 or 3x3 or 2x3 or 3x4 or 2x4 or 1x4. So you could run it basically in that or any combination 3x3, 1x2, okay, because it has a total number of 16 addressable keys. So you cannot use more than 16 keys. You have to find another IC for that. Now the output enables the output of this address, the 4-bit address of the keys, and the data available is, this is the pin that returns logic 1 when any key is pressed. So once the key is depressed, so nobody is pressing the key, then it would return to logic 0. This is the address table for the 74C922, which shows the address of the keys in column 1 and the 4-bit address here, column 2. So if you press switch 1, it returns the address 0000, or if you press, say for example, 9, the address is 1010 in binary. So the rows here, or the keys here that's colored yellow, these keys cannot be accessed if you are going to use a 3x4 keypad. That's because in the 3x4 keypad you don't have the 4th column, so therefore any keys in the 4th column cannot be, or the address of the keys in the 4th column cannot be addressed. So you cannot, the 74C922 could not generate that address if that 4th column is not present. So you just have to analyze the data output. It's basically just sequential from 0 to 1111, or from 0 to F. This is the schematic diagram if we are going to use now the 74C922 keypad encoder. I want you to focus your attention here because the keypad is no longer connected directly to the microcontroller. It's connected to the keypad encoder. So you have here the X and Y. It's connected to this part of the keypad. And if you notice that pin number 7 is blank because there's no 4th column. And these are the 2 capacitors that's required for the keypad encoder to function properly. So you have to place the capacitor at the oscillator pin number 5, at about 0.1 microfarad, while KB MSK, pin number 6, should be 10 times the size of, or 10 times the capacitance of the capacitor connected at OC, pin number 5. So that's 0.1 microfarad. The DAVBL pin number 12, is connected to an inverter, which the output inverter of the inverter is connected to output enable. so that when you press any key, the AVBL will be 1, inverted, becomes logic 0, which is connected to output enable, which is to enable the output enable pin, or pin number 12 or 13 should be logic 0. So the moment you press the switch, the AVBL is 1, and then you invert that, and then OE is now equal to logic 0, so that the 4-bit output in pins 14 to 17 would be, there would be an output here. So you can now read the keypad address, the 4-bit keypad address here. Okay, so in this particular example, we have a 7-segment display, but this would be for later activity. So how do you read the 4-bit data from the 74C922? Well, according to the flowchart here, after configuring all the I/O ports, you have to read the DAVBL, because that would be the signal to read the keypad data. Now, without the DAVBL, it would be very difficult to read the keypad data, because remember, if you just rely on, say for example, if you assume that when there is no key press, the 74C922 would just return 0000. Well, it's not going to return that. It's because 0000 is the address of key number 1. So therefore, we should have a distinction between the keypad data 0000 against any, or against a keypad where it's not any, where none of the keys are pressed. So that's where the AVBL would come. The AVBL again would get to logic 1 if any of the keys would be pressed. So that's why here we read the AVBL and then evaluate the AVBL if it is equal to 1. Otherwise, you continuously read the AVBL until the AVBL will be equal to 1. And then after that, that's the time you can now read the 4-bit data, and what will you do with the 4-bit data would now be here in this particular process. Okay, now the software control in the previous slide shows that the keypad data will only be available if the AVBL is high. So the software basically will continue to read the AVBL and only exits the loop when the AVBL will be equal to high. Now the worst case scenario here is that what if nobody would press the switch, or nobody would press the keypad. Therefore, the microcontroller would be stuck in this loop here, and the CPU is not doing anything. No? So the solution to that, of course, it's not efficient, but it works. But there is an efficient solution for that problem, where we want the CPU to perform other tasks other than just waiting indefinitely for a key press. One method is the use of external interrupt, which will be discussed in Unit 5, but I think for those of you who are under me during the transition SEM about the PIC 16F84, we use the timer, the RB0 external interrupt as the interrupt source for the keypad. So that's the same method. No? So the AVBL will be an interrupt source, so that every time the keypad would be pressed, or any key would be pressed, it will just generate an interrupt to the CPU. And the CPU, with that interrupt service routine, will just read the data of the keypad. That's it. The CPU will just return to its normal operation. Another method is to use scheduling, which will be covered in Unit 8. The scheduling is different from interrupts because the keypad would be read at a certain schedule, certain interval. So there is a schedule for reading keypad data. So you don't have to, the CPU does not have to wait for an interrupt, but the CPU would have to make sure that the schedule will be followed. Otherwise, there would be a miss. No? So you could no longer read the keypad, the key press, or the keypad data. So if you press the any switch or any button on the keypad, that would be ignored by the CPU if the schedule is delayed. So that's the downside with this scheduling, but it does not require any interruption of the CPU. So we will cover all of this in the succeeding chapters, in the succeeding units. But for now, the method earlier is our best uh, choice for reading the keypad data. So let's just well, if you want to have fun, so well, I can throw this sheet to work for you, but this should not be submitted. So you can draw a flowchart for a program that will display the key being pressed in a 7-segment display. Keys, asterisk, and pound will do nothing. So refer to the schematic diagram here, where whatever the key that is being pressed, you just display it in a 7-segment display, which is connected at port 1, port 1. So we don't have any decoder here, so therefore you have to decode the you have to basically decode it yourself, in software, so you can display the uh, the digits here representing each of the keys in the keypad. Again, this is not uh, for submission, but if you want to do this, okay, you can do practice. You can practice because it might come out during the midterm exam. Who knows? It might. So again, the same expansion board as with the LCD will be used. And if you want to know more about the 74C922, just download the 74C922 datasheet. You just download, you can find it on the internet. There's a lot of resources for that. So that ends our lecture. Thank you very much for listening, and see you next time.